Hi, everyone. My name is Hideo Joho. I will give probably 45 minutes presentation on mainly on such interaction. So a little bit about myself. I'm associate professor at the Faculty of Library and Information Media Science at the University of Tsukuba, which is in Japan. If you're interested in my personal performance, you can look at Google Scholar, and if you want to tweet, that's my account. I did my master's and PhD from iSchool in University of Sheffield, which is UK. And Eric and I worked together while I was doing a postdoc in Glasgow. After that, currently I lead two organizations, which is one is the Tokyo ACM SIGAR chapter. SIGAR is the largest international conference community in information retrieval, and the Tokyo chapter is one of the local chapter, and I have been the chair of that organization. I also recently started a new research unit within the University of Tsukuba, where we have over 20 researchers in Japan and abroad to collaborate together on information retrieval and recommender systems. So as you can see, my research interests are information retrieval, especially on the user side. And recently, I've been working on conversational search and live logging search. So for the both topics, as I showed there, I've been organizing a series of international workshops in the last few years with the leading members in industry as well as academia. On the professional activity side, I've been a program co-chair of Chair 2019-21 and other conferences. I also have been associate editor of Information Processing and Management, which is one of the major academic journal in information retrieval field. So that's me. So what I'm going to talk about today with you guys is about search engines and how AI technologies impacted the search engines and search interactions. And I will present some of the visionary scenario where some of the AI technologies can even enhance how we do the searching. So hopefully we will learn something from my talk. Let's start with the scale of search engines. We all, every day we use search engine, right? But we don't quite know how many queries that we're submitting in total. This is statistics from kind of investigations companies. Some of them official figures from Google, some of them are through the accounting companies and so on. But this is it, right? So last year, Google got 5 trillion queries. And when I created this graph 2 years ago, it was in 2019 or so, it was 2 trillion. But the number has been more than doubled in the last 2 years. So we have a huge number of queries submitted, and this is the scale of the search and search engines worldwide. And in terms of the economic impact, back in 2009, which is more than 10 years ago, McKinsey did some estimation of the economic impact of the search industries, and they estimated as 780 billion US dollars on 2009, which is less than 10% of the number of queries that we Google processed every day. So you can imagine how big that is currently. And for your reference, for example, Olympic, which may happen or may not happen in Japan this summer, is around 300 billion US dollar in terms of the economic impact. So you can imagine how big these things are in search industry. And maybe some of you have seen this or may not have seen this. This is one particular aisle of the Google's data center where each of those slides is a PC. And so when you submit to Google, when you submit a query to Google, or when you submit contents to YouTube, whatever on the web, thousands, millions of PCs have been processing your contents and serving for your queries. So this is scalability of search that I'm going to talk today. So what we know, I'll explain some of the glimpse into this 5 trillion searches, that search behavior that we know, which is about your behavior every day, to be honest. So one characteristic is that we submit very short queries. This is the figure from 2006 survey paper by Jansen and Spink, illustrating proportion of single query, just one word queries across the few years of search engines. This is old, but basically our survey, recent surveys also suggest that this is basically true. So as you can see here, between 20 and 50% of queries that people submit only just one single term, right? And if you took out a bigger proportion of the queries, then we know that between 60 and 75% queries is less than 3 words. So you can, reflect yourself how many words your last queries consist, right? And usually it's very short. Having said that, we are a minority. We submit like the journal title, paper titles, really long queries. So we are nightmares for search engines, but generally speaking, general audience people submit very short queries. This is the first our search behavior. Second search behavior is that we have super biased, ranking biased click behavior. So this is statistics from the top ranked documents, the 10th and actually 11th, which is the next page, documents. And the thick gray bar is how many times people clicked. And the narrower black line bar is how much we see by our eyes. So if you look at the narrower black bars from the top of the results, it's kind of nicely slowing down, right? It's a monotonically decreasing line, which makes sense. But if you look at the wider, thicker gray bars, then you can see that top second position in the search result is like less than quarter of the nearly quarter of the click rates. So which means if you are an e-commerce website, e-commerce companies, if your position for that particular query is the second and first, you have a huge difference of incoming traffic. So we are very much biased on clicking the top result. So this is the second pattern that we know. Third pattern is where we're looking at from the website. So this is also, we call it heat map, and it illustrates where we're looking at in these web pages. So the frequent position that we look at, it becomes red, and if we rarely look at it, then it gets gray. Right? And the right side one is a Google web search engine. And if you look at these patterns, it looks like a little bit like F shape, letter shape. Maybe because I said that, right? But this is also another typical behavior that we know when we look at search engine result page, which we call it SERP. People look at in this F shape patterns. So what does it tell you is that if you were to put the important messages or advertisement in a Google search result, you shouldn't put the right bottom of the page because no one look at it, right? You should put it left top of the screen. So this is the third pattern that we know. Recently, you've probably noticed that the Google puts a lot of direct answers or card or knowledge graph. People call it a different way. But basically, it's a piece of block text where they try to answer your queries directly rather than navigating you to click the URLs to find answers. So the recent study by Wu and her colleagues show that people do look at these direct answers quite a lot. And more they look at it, or the more answers that they show on the search engine result page, then people click less on the organic search results. So this is relatively new findings because the use of the direct answers, are relatively new. So our behavior changes when direct answers are shown when compared to the interface that are not having a direct answers. What about ads, right? We see ads all the time, and some people find it annoying, some people find it useful. One of the well-known behavior is we call it banner blindness behavior, which is can be seen here. Again, this is eye tracker, so they're tracking where we're looking at on the website. And as you can see, they look at query box, and after that, people nicely skip the ads area and then go to the direct answers, and then goes to the query suggestions or question suggestions, and then go to the top result and so on. So because we used to it advertisement a lot, we kind of unconsciously skip this advertisement. However, we have very interesting recent study this year, actually, by Cheer. Researchers from Strathclyde show that different impacts of the advertisement on our search behavior. For example, if you look at the middle bottom things, for example, even if you have ads or not having ads, it doesn't really quite change the level of tiredness, or it doesn't really affect the confidence of your decision making. Or it doesn't really affect, you're not that confused or anything. Or you don't find either of the web pages more, aesthetically appealing or not. On the other hand, if you don't have, if you do have ads, then we are more frustrated, right? Which you can probably agree. And funny thing is that you're more likely to feel the web page annoying, but also apparently people feel that the web search engine result page with advertisement are more engaging or less boring, right? So there are a lot of things that we didn't know before. For example, the effect of advertisements. But the showing advertisements are not only negative things, but also apparently there are some positive things that probably we didn't know before. Okay, so I've shown scale of the searches, which is a 5 trillion queries, and I've explained some of the basic behavior pattern, which is really short queries. We are super biased on ranking. We look at top-heavy search areas. We spend a lot of time on direct answers when it's shown, and also advertisement apparently have some positive effect, although there are some negative effects. So these are the some of the search patterns, interesting search patterns of 5 trillion queries. Let's move on to let's move on to today's main theme, I suppose, is the impact of AI on different applications. And of course, I'm going to talk about applications on such interactions and such technologies. So the easiest example of deep learning technologies and AI technologies made on our behavior and technologies is voice input. And technically, this is called automatic speech recognition. And this is one of the earliest successful application of deep learning technologies where they made a huge improvement over the state-of-the-art things. And be able to input words via voice or speech is great for mobile devices or smart speakers where your hands are tied. If you're interested in, you can look at that website and nicely explaining how our voices are turned into a neural network, and then from there to the actual words, and how deep learning techniques are used to improve this inference process. So okay, you can speak to your mobile phone instead of type, and how does it change, right? In 2016, Google said already 20% of search on the Google app are submitted by voice, right? It's a large number of a proportion of queries that have been voice queries. And it's 2016, so naturally you can imagine that this number is increasing. But the funny thing is that the voice queries are also quite different from when you type. So this is a funny thing, right? I mean, because if you think about it, you're after all typing a keyword, right? After all, you're inputting the keywords, and one is you use keyboard or things, and then one is speaking. And how come this can be different, right? I mean, you just modality is different, but how come that manifested to the different queries? But they are indeed different. And Guy back in 2016 showed that several patterns like this. And on your left side, as I explained earlier, that our queries are short, right? Like less than, in this case, over 60% of text queries, typed queries, are less than 3 words, right? But if you look at the red one, which is a voice input, it's kind of nicely, the peak is on the right side, right? Which means when you input queries via voice, we are likely to type more words. Our input words are longer than typed. Why? We don't know why. But this is an interesting pattern, right? And also, if you look at when you type mobile phone and when you speak to the mobile phone, right? So this is a time hour distribution on the right side of the figure, and show that in the morning you're more likely to text input, while after like I don't know 10 a.m. to 8 p.m. you're more likely to speak to the device than text. And maybe after 8 p.m. it gets in the evening, you don't want to make a noise, so people start to type again and so on. So what does it mean is that when you look at such interactions and using a deep learning technologies, it's very important to think about how to diversify the search experience and how you communicate with search engines, how to express your queries, how to browse the search result, and so on and so on. And this is what I am very fascinated about it, and I'm going to talk a little bit about it. But this is one very clear example where the deep learning technologies improve the speech recognition technologies, and that allowed us to input queries in voice. And at the end of the, as a result, our behavior was quite different from the typed queries and so on. Second example is probably a little bit about deep learning, but largely more about like machine learning technologies applied to such algorithms. So we call this as a whole domain where we apply any sort of machine learning technologies to the ranking problem. We call it learning to rank. And before learning to rank, the search engine used to apply the same basic rules to all queries. So this is a screenshot from Wikipedia, and maybe you have heard of ranking algorithm called BM25 or TF-IDF. The formula equation might look a little bit clumsy and slightly complicated, but if you look at it, it's actually fairly simple. You're just basically counting only 3 things, right? And one is what we call it IDF, which is how many documents that query has got in the entire corpus. And one is the term frequency, which is how many times that query appeared in a single document. And the third component is just the length of the documents, right? And you have like average document lengths across the entire corpus and so on. But it's just the term frequency, document frequency, and document length. Those 3 things are the only thing that actually variable within this BM25. And all the queries and all the documents, same old, let's say weighting scheme have been applied to the ranking. So this is the before learning to rank appeared. But still, the funny thing is that such a simple algorithm is very strong and works really well across different applications and domains. So still, we use BM25 as a baseline in our experiments. But what I like you to understand here is that we are just using the same rules to all queries before learning to rank. And this has been changed with the learning to rank. Search engine now applies different rules, which we call it weights, to document features for different queries. So I'm not going to talk about details of those algorithms, but I'll give you some examples. For example, if a user typed long dress, then you can imagine that the shape of dress is more important, right? So the shape features of the contents should be weighted higher. While the query was red dress, then you can imagine that the color feature of the contents or product is more important than shape, I guess, right? So in this way, in learning to rank, machine learning techniques are used to learn kind of optimal weights from the past click data. So you have the long dress and this document was clicked, and then think about, okay, why this document was clicked? What features were prominent in this document compared to the other non-click documents and so on. And by doing so, you can slowly learn that for this query, this feature is important. For this query, these features are important, and so on and so on. And again, you use a huge number of 5 trillion click data to train your classifier. So as a result, for example, when people submit the query like summer dress, now can you imagine what features are important? It's a difficult answer, right? It could be a shape, it could be a texture, it could be a color, it could be a mixture of those things. And we don't know whether is a texture is more important than color, or is a color more important than shape, and so on and so on. With the learning to rank technologies, we can deal with these complex queries or complex relationship distribution of the weights across the document features. So this is the kind of second example where machine learning techniques and deep learning technologies have changed the way that the rankings are made. And if you're interested in this kind of topic, Liu and Lee both have got really nice textbook focusing on the learning to rank for information retrieval, so it's recommended. Now, the third one is BART, and if you're in NLP domains and machine learning domains, you don't have a day without hearing the word BART and his their family. And previous speaker also mentioned about these things. So I don't think I need a lot of explanation for this, but if you don't know it, the BART is a generalized language model trained with a huge corpora. And it stands for bidirectional encoder representations for transformers. And Google doesn't say doesn't often brag about their technologies, but when they do it, they do big. And then when they released BART, they said that this is the biggest leap forward in the past 5 years, and one of the biggest leaps for the history of search. So they're quite confident, right? They're pushing it a lot. If you are interested in how BART works, then if you search for like BART explained, then there are lots of kind of nicely illustrated things and so on. If you're super new to this technology, then I would suggest to start learning from word embeddings and the recurrent neural network, or LSTM as an example of it. And then move on to transformers and encoder-decoder architectures, and then go to BART or backwards. The Jimmy Lin and his colleagues wrote a really nice book focusing on how to apply BART to the ranking problems. So this is a highly recommended book. Now, what are the examples of BART applying to the ranking algorithm? So this is one of the best algorithm where the BART has been applied to the ranking issues, which was presented in SIG-IR last year, which is called CallBART. I mean, there are many algorithms. I'm just showing one example. And one of the characteristics of applying BART to IR is that in information retrieval, your queries are always dynamic. You don't know what queries people submit until you get it, right? So if your algorithm were to calculate the relationship between queries and documents in a network like the C model, then actually it takes ages to get back to your result. So one of the things that the CallBART did in terms of the architecture was that they separated the query network and the document network. And the document network part, you can do it in advance, right? So you don't need anything to do in the query time. And when a query is submitted, it needs to be converted to the bot, but only you do the max similarity between the top layers, between query models and document models. And surprisingly, this is super simple, but it worked really well. So you don't need to know the details about this table, but let's say this is the top row is the BM25 that I mentioned earlier, and that was 16.7. And with this Colbert algorithm, the score is like more than doubled to 34.9 on MRR at 10. Now, you don't need to worry about those units and evaluation metrics, but as you can see, the bot is super effective and changed the research landscape in information retrieval completely in the last couple of years. So these are the some of the examples where the AI changed our search interactions as well as search algorithm. So if you're interested in, this is really hot topic. If you're interested in, go for it, look at it. Now, the last part of my talk, I will present some of the kind of ideas where AI and deep learning technologies can change the way we do search. So I'm going to talk a little bit about future vision of this idea, and then I will explain some of the architectures and key components as well as challenges. So this is my future vision. So let's look at the left side, which is what we are now. You guys are now. You guys are watching or listening a lecture, right? And maybe not, but maybe you come across some unfamiliar concept that I said and you've never heard of, right? And you wonder what that is, and you fetch your mobile phone from your pocket, or you start to type with the keyboard and type queries. You get search result from Google. You browse search result. You click URL, and go to the web page, and finally you get the information, right? And then while you do all that, lecture have moved on, and I'm talking about something different. So this is what we are now. Now, I'd like to change this situation to the right one, which is, again, you're watching my lecture or other lecturers, and then you come across unfamiliar words or concepts and wonder what that is, and magic happens, and you get that information about your answer, and you stay on course. You never lose anything. So this is the future vision, and you can see how our information obtaining interaction mode is different, right? Now, here as an example, I'm just showing watching a lecture as an example, but this vision of skipping in the middle, automating queries, searches, can also be applied to when you're reading a book, listening a podcast, writing an essay for your assignments, or talking to a stranger, any sort of kind of intellectual activities that we do every day. Okay, so not just watching things, but I do a lot of examples from this one. So what is it? What's the vision that I'm talking about? From the search point of view, this is a personalized search because this is why this is personalized search. Well, because the unfamiliar concept that you might find from my lecture is different from other people, right? Other people will find other different words unfamiliar, right? So everyone has got different knowledge state. So everyone will find a different word unfamiliar. So my idea is to get information that is relevant to the information that is missing from your knowledge state. So this is pretty much personalized search. And also, as I said, and here, because you do not really submit any queries, you just listen to my talk, you just wonder, I don't know what that word is, and you get that information. So this is a real-time search, right? It's a sequential and real-time search. And also because you don't submit a query, this is called zero query search. You don't type any queries, right? So this is what it is in terms of my future vision. Now, why does it? I mean, I hope you guys find it kind of interesting about this idea. But if you're not, don't worry. Let's put some more ideas. And why does it matter? Now, do you remember that we talk about 5 trillion queries, right? 5 trillion searches every day. Sorry, every year. Now, let's assume that you come across an unfamiliar word, you fetch the mobile phone from your pocket, and you type the keyword, right? And let's assume that it takes as swift as 3 seconds to do all that, right? And that's 5 trillion searches, so about 15 trillion seconds, right? And 15 trillion seconds is like 11.4 billion hours. Million hours a day. And every day, right? 11.4 million hours that you're spending to type the keyword. Now, let's multiply by the minimum wage in US, which is like $7.25 a day, 1 hour, sorry. And if you multiply that, then that's $82 million a day. And let's imagine that just 10% of our typing queries, that's 8 million US dollars a day. So why does it matter, the future vision that I talk about? Why does it matter? Well, because if we are able to automate 1 in 10 queries, right, just 10%, 1 in 10 queries, then we can save $8 million of labors every single day, right? You can check my math. I may be wrong. I might lost a couple of digits. I don't know. You can check. But just many queries, many searches you do every day. If I can automate only 1 in 10, we can save $8 million every single day, 365 days, right? Which is a huge money. So that's why it matters. Well, in a more serious sense, why this matters? Well, as you can see, as you can imagine, as you are told many times, that the world changes faster. The change rate is much faster when I was your age and I was I was doing master's students or PhD students with Eric, right? And we call it VUCA, right? If you don't know the word, just look up the word, right? I hope the things will be automated, but not now yet. So just look up it, and it's a VUCA, right? And what it means to your career, there are many things. One is that the knowledge and skills that you acquire today will expire in 5 to 10 years. When I was younger, at your age, our skills and our knowledge lasted, let's say 20 years, 30 years, right? That's why your professor is still professor. But in your generation, unfortunately, because the change rate is so fast that your knowledge and your skills will expire in much shorter span. What does it mean? Which means every 5 years, every 10 years, you have to start from scratch. You have to completely revive your knowledge set, skill set, right? Because it's no longer, needed or obsolete. What does it mean? Which means we need to change how we learn. We need to change how we acquire skills, how we acquire basic knowledge, and so on, right? So the learning process also needs to be a lot faster. So the future vision that I explained, I illustrated, are one of the components where it helps you to learn new things, unknown things as fast as it should be, right? The second aspect is, as you've been interested in and probably working on it, is that AI technologies sooner or later will replace general task where it's a common task because we have lots of training data. Sooner or later, AI will learn the basic, learn the patterns, and then they start to perform better than we do, right? Like chess and lots of games. Which is, some people find it, a bad thing. Probably you guys find it exciting thing. But what does it mean? Which means we don't do any general things anymore. Which means every single one of us becomes a domain expert. And you're expert and I am expert, and we're expert on a different thing because we don't need to do general things anymore, right? Now, which is a great thing, which is a creative world, which is free world, and we can spend a lot of time on what we're interested in, because of AI technologies can replace our boring stuff, which is great. Now, if you think one step further, what happened is that the communication between two domain experts who are completely different area, but they have to work together to solve significant problems, they have very limited common grounds to communicate. We can communicate a lot of things because we have a lot of common ground between us, right? But if you start to think about everyone is a different domain expert, right, in the future, then our common grounds to communicate will be very limited. Again, that means we need to learn each other very quickly. So let's imagine my communication with my daughter, 10 years old daughter. She's an expert on 10 years old. I'm an expert on 40 years old, right? We're expert in our own domain, but I have no idea what she's talking about, right? I have no idea what she's excited about. Why? Because, I don't understand many of the vocabularies that she's using. So it's the same thing, right? Different domains, different culture, different generations. We need to pick up words. We need to pick up concepts which separate us very quickly. So this kind of automated search, I believe, is in place to help facilitate the communication between the two very different domain experts to solve huge complex problems. Now, I hope I sold my idea that this is important and this potentially helpful for the future world. So how does it work? Well, this is a very simplified architecture, but you have on the left side the users, and users doing work with the, let's say, smart devices, that I call it. That smart devices needs to have a human sensing, what we talk, what we read, what we listen, and so on. And this human sensing will extract semantic information from our behavior, send it to the knowledge modeling components. And that knowledge component modeling needs to be updated all the time as we speak, as we read, as we write, as we listen. And that knowledge component also formulate automatic queries automatically, submit to search engine get the result, and let's say send back to the smart device. This happens background all the time, right? They are with us all the time. When you're reading a book, when you're listening to talk, you realize that, oh, I don't understand that word, right? So in our world, it's called a knowledge gap. They recognize a missing knowledge. And when that knowledge happens, people behave the seeking behavior. They show the seeking behavior. And the smart device will detect that and present the information which was retrieved in the background by the search engine. The search result, maybe we like it, maybe you don't like it, but those relevant feedback will be sent to the devices and knowledge modeling will update, oh, this person didn't like this information, or this person already knew this information, and so on. So this is a simplified architecture. So we have a users and some sort of smart device, and we need a human sensing technologies, and we need like a knowledge modeling components, and as well as the search engines and so on. So I will give a little more detail on some of the components. One is capturing human senses. So, as you know, we have like eyes and ears and touch and smells and taste and those 5 senses. If you look at proportion of the information that we are getting, actually the eyes and ears constitute of like 75% of information that we're processing. And although touch and smells and taste are important, but in this talk, I will focus on eyes and ears because those are the majority of the input information. So what are the smart devices? Well, our best candidate at the moment, there are many experimental devices have been developed, but our best bet at the moment, which we can buy, is a Microsoft HoloLens 2, which has got head tracking, so they know where is it looking at and so on, and we have the eye tracking. They have the hand gesture tracking, so if I do this, they recognize which fingers and so on. They have the world view camera, so they have a view camera here looking at ahead, so which they can get the picture of what I'm looking at. And also they have a 5-channel microphone to pick up what I'm hearing or what I'm speaking. And finally, they have this see-through displays to overlay the, let's say, search result on mixed reality domains. It doesn't have to be this one, but I use it this as an example to illustrate what I'm talk about next. So how does it help us? This is just one very simple example because it's easier to understand. So let's imagine that you're putting those, HoloLens 2 and you're reading a book, right? And this blue area is the scope of the world view camera from the HoloLens 2. They have much bigger view. And the red area is the one that our eyes are actually looking at. Right? And if we can camera follow what I'm reading at the moment, you can run it to OCR, you can look at object detections, those technologies to extract the semantic information. HoloLens get that, send to the Wikipedia, get the basic information, and showing to the users, right? Another interesting thing we can do is because this camera view is much bigger than the user's view. If users are on this orange box, we know that these guys will come to the rest of the moves, to the rest of the pages, right? So which means we are few seconds, 10 seconds, 20 seconds ahead of this actual user. So we can prefetch contents from the remaining area of this book, and we can do a lot of intelligent things and wait for users come to the point, and then we present interesting searches. So this is one example where we can automate search. They're just reading a book, they recognize something that's missing, and when they recognize it, the information is presented, right? No queries, no asking, nothing. So in order to achieve this, there are many challenges, but obviously one of the things is that how can we model my knowledge state, right? How do they know what is missing, what is not missing, and so on. Well, some of the idea is is this, that I use BART, which I presented before, as a knowledge state, also known as a user profile. So as you might know, you may not know, the BART is a multiple layers of neural networks, and sentences are coming in to update the weight of the nodes in every layers, right? And the typical use of the BART is that you have a huge corpora, and then you train the BART model, and then you do what we call fine-tuning to adjust this general knowledge language model to specific tasks. But what I'm suggesting is that we just keep this pre-training, keep training, right? So when you do intellectual activities while with the HoloLens 2, reading, listening, and so on, we will extract, converted, many things to the strings and text, and that will feed into the BART models, and the BART model will keep updating its model, and eventually that becomes your BART. It becomes a BART which represents your knowledge state. And you might find this idea ridiculous, but I'm not the only one who's talking about this. And last year in ACL, one of the papers actually indeed demonstrated that this kind of idea works, that they said don't stop pre-training. And you have the trained model with the web text, but you don't stop there. You put the web reviews text, product reviews text, Amazon's review text, and Amazon's book review text, and so on and so on. And you can actually make this language model to be adaptive to the tasks and domains and so on. Which means, this is a very generic process and a lot of text, but the basic principle is the same. You can use BART as your knowledge states if you imagine that this is a kind of personalized input data rather than the general corpus like this, right? So what were we talking about? Well, we are talking about automating search, right? While you're listening to talk, reading a book, listening to a podcast, writing an essay, your smart devices pick up the semantics from there and then update your knowledge states, and you get the search result in an automatic way. So what is this again? Well, this is knowledge state modeling. This is a knowledge augmentation because they automatically augment the knowledge that's missing from you. It also, I hope that it's, can be used to evolutionize our learning process and also communication with the people who have very different domain, experts and so on, because we need these things in the future. Okay, so I'm running out of time. So what are the challenges? Well, edge computing power needs to be much more powerful than it is now, right? The HoloLens 2 is great, but there are many things that are still picking up. Also, object detections of the views, speech recognitions, motion detections, those needs to be more advanced. The biggest challenges is how to model our knowledge state, right? User knowledge modeling. And also, based on those knowledge states, we need to develop such algorithms and such interactions, what's the best way to present such results to the users, and also how we keep the privacy and how we even evaluate these technologies work. So there are many challenges, and which is an interesting thing and a promising thing. So, okay, so this is my last slide. Search is a 5 trillion annual data points research area, which is fascinating, huge. So hopefully you're interested in this area. Lots of interesting insights into our search behavior already. AI has changed some of them, and probably will do so more in the future. Sensor-based automated search that I explained is one such area where very interesting deep learning application can be used to change how we search, how we obtain knowledge, and how we communicate. And, this is not Eric one. I will actually do that. This is you guys, young generations are the one that who, make this all innovation true. So what's important is that I presented one vision. You may agree, you may not agree, but what's important is that you develop your vision, right? And then you acquire skills, think about what skills needed to achieve that vision, right? And then achieve it, right? Okay, this is it. Thank you. I'll stop here.